and welcome to our science education series at Virtual Regeneron ISEF. I'm Caitlin Sullivan, the Director of Outreach and Equity Programs at Society for Science and the Public, and I'd like to welcome you to these series of symposia that are focused on supporting students in scientific research. This particular symposium is addressing a topic that is very important to student research, but that many students and teachers struggle with. And that topic is statistics. So I have joining me today Dr. Paul Strode from Fairview High School in Boulder, Colorado. Welcome, Paul, and thank you for being our guide in this crash course in statistics. I'm going to turn it over to you.
Well, thank you so much, Caitlin. What a thrill it is for me to get to present at Virtual ISEF 2020. And so I've been attending ISEF since 2006 in Indianapolis, off and on for the last decade and a half. And I think this ISEF would have been my 10th. And I've given shop talks over the years. This is a smashed version of a talk I gave last year. And so my goal here is to talk about uncertainty. Not to get too much into the weeds of inferential statistics, but just talk about what students need to know when they are just getting started in understanding how statistics work and how to quantify uncertainty. All right. So Caitlin, I have a question. Do I need to push to audience?
Yes, you should. Thank you.
Okay. All right, so I have two focus questions here for this talk. What is the role of uncertainty in science, and what are some simple steps towards quantifying uncertainty in a sample? And so what you see here are four images. These are 5 of my science research students this year. Here they are presenting at our regional science and engineering fair, and they all gave me permission to use their images. And so in the left here, that is Jason, and he's presenting some data in a very traditional way. He's using column graphs with those are standard error of the mean error bars. And then on the right, that is Helena and Sierra, and they're showing some frequency diagrams of their data with some dashed lines in the middle to indicate the means. The lower left-hand corner, that's Sarah, and she is showing the distribution of her data in a Gaussian distribution. In the blue is the standard deviation, plus or minus 1 standard deviation, and so she's showing her uncertainty that way. And then in the lower right-hand corner, this is Kimberly, and she's showing something that I'll come back at the end and talk about, where she's really showing a lot of great data visualization. She's got box and whisker plots. She's got means with 95% confidence intervals, and then she's got stacked dot plots with some jitter. And so anyway, that's where we're headed in this short talk. So I'm assuming that since you're here and you're involved in ISEF, you have a pretty good idea of what science is. But just to be clear, here is the National Academy of Sciences definition of what science is: the use of evidence to construct testable explanations and predictions of natural phenomena, as well as the knowledge generated through this process. And so I have a list of all of the best practices of doing good science in green there. And then in red, that's bad science. So those are things that we often we forget about, we might do poorly. And so when we're doing any one of those things, we're actually doing pseudoscience. And what I want to focus on here is at the bottom, and that is measurement uncertainty. And so if you're doing good science, you've got transparent measurement uncertainty. You're reporting it. You're being very careful in how you're calculating it. But if you're not really doing good science, then you've got limited uncertainty. It's faulty. You downplay it, or you're just missing it altogether. And so that's what we'll focus on. So our first focus question is, what is the role of uncertainty in science? And so we know that science is in large part a pursuit of accuracy and our understanding of what's actually going on in the natural world. But there will always be some level of uncertainty, and that's something that I think a lot of people in the general public really don't have a good handle on. So one of the most important things we do as scientists is to quantify and report that uncertainty about our claims and predictions. So this is so important that our national labs across the world have guidelines for their scientists on how to quantify uncertainty. So here are just 3 examples. Here in Boulder, we have a branch of the National Institutes of Standards and Technology, and they have Technical Note 1297, guidelines for evaluating and expressing the uncertainty of NIST measurement results. In Canada, the National Research Council of Canada has an introduction to expressing uncertainty in measurement for their scientists. And then in the United Kingdom, the National Physics Laboratory has their beginner's guide to uncertainty of measurement. And of course, they have a fun little image there about how slippery it is to do measurements and quantify uncertainty. So it's critically important. To put this in context of something that might come out of a governmental lab, like the National Climate Data Center or something like that, here we have the Charney report from 1979. So this is over 40 years ago, where they say, and you can see in the red box there, probable global warming for a doubling of CO2 to be near 3 degrees Celsius with a probable error of plus or minus 1.5 degrees Celsius. So they are reporting their uncertainty. And then fast forward to just last year, Marcia McNutt, then president of the National Academy of Sciences, wrote in her editorial that they were pretty much dead on that prediction. She says, fast forward to 2019, and these calculations of the sensitivity of climate to a doubling of CO2 have proven to be remarkably on target. And so if we do a good job quantifying uncertainty, we can really make some important predictions. But when we look at how our reports of uncertainty are understood and misunderstood by the general public and even our policymakers, we see that there's a lot of trouble, I would say. And so here are some images from the 2014 Intergovernmental Panel on Climate Change report, where they're showing lots of figures with data and with predictions and with uncertainty measurements. And to expect a policymaker to understand these, I think we should expect them to, but they're not all trained in statistics, and so we end up with trouble, like James Inhofe holding a snowball on the floor of the chamber, saying we keep hearing that 2014 has been the warmest year on record, and so anyway, we'll come back to that. So when you dig into some of these reports, you see that they do provide some guidance for these policymakers on uncertainty, but they're buried in footnotes and they're buried in figure captions, and I think we're asking quite a lot of them. So as we fast forward now to focus question number 2, what are some simple steps toward quantifying uncertainty that can function as a starting point for students who are first learning about science research? We have to understand the relationship between statistics, or between sampling, which is what we do, what we apply statistics to, and the populations that we're trying to make predictions about and trying to understand. And so I have a figure here that shows this relationship. So on the left is the population with these unknown parameters that we're trying to make sense of, and we use some kind of unbiased sampling method, randomization or stratification. We take a sample, then we use statistics, mean, variance, inferential statistics, and we try to make inferences and predictions about these unknown population parameters. And we just go back and forth and around trying to make sense of what's going on in the world. So what do I do in my classroom is I start my students with the very basics, and as the title of this talk says, I peel back the curtain on statistics, and I have them calculate everything by hand for quite a long time until they really understand what's going on behind the scenes. And so we're going to just take a quick romp through some imaginary data here, and how we actually go from the sample to some of these assumptions we can make about populations. And so here we have two sets of data. These are data of Crofton seeds. This is a weed seed. And so we've taken 25 seeds and put them in each of 10 Petri dishes and put those dishes in the dark. And then we've taken 25 seeds and put 25 seeds in each of 10 other Petri dishes and put them in the light. And so the odd Petri dishes are in the dark and the even ones are in the light. And then we just let them go for 72 hours and see how many of the seeds out of 25 in each dish has germinated after 24 hours. And so you see the data for the dark treatment and the data for the light treatment, and then you see the means at the bottom. And then you see all of these crazy statistical terms as well that we'll talk about. So again, why do we take samples? Well, we're trying to estimate some theoretical parameters of the population. We can't measure the entire population of Crofton seeds out there, so we take this sample. And because it's a sample, our estimates of the population are plagued with error and uncertainty, so we need to quantify that. And so here are some of those statistics that we use. These are all called descriptive statistics, so they're describing the sample and they're allowing us to make some kind of an estimate about the population. Before we really dive into these calculations, I just want to say a few things about degrees of freedom, because that tends to be something that is not well understood by teachers and, of course, their students. And so the question here is, what is the relationship between n, which is the sample size, and df, which is the degrees of freedom? Now, if we had lots of time, I'd have you talk in little groups about this and try and come up with answers, but I'll just give you the answer here. So before any measurements are taken, every measurement has the ability to vary within some maximum and minimum. And so our sample size and our degrees of freedom are equal. So in each of these treatments, the dark and the light treatment, all 10 of the measurements can vary before we take any of the measurements. However, once we calculate the mean, now we know something about the sample. We know a parameter of that sample, and we have lost 1 degree of freedom. And so if we were to recount all of the seeds in those Petri dishes, we take dish number 1, and we count the number of seeds, and that can vary among all 10 dishes. And then we take the second dish, and now that can vary among the remaining 9 dishes. We count the third dish, that can vary among the remaining 7, all the way down to the 9th dish. That can also vary, but the 10th dish can't vary because we already know what the mean is. And so once you calculate this very first statistic of a sample, you've lost 1 degree of freedom. And so that's where n-1 comes from. But there's also another important reason for n-1 that I'll come back to in just a minute. All right, so the second calculation we make is called the square difference. And so in this case, we take each of the measurements. So for example, in Petri dish number 1, we have 12 seeds that germinated in that dark treatment. And we find the difference between that measurement and the mean. So 12 minus 9.6, and then we square that difference. And we do that for every single measurement. So why do we do this square difference? Well, we do it because we want to amplify the big differences. We want to give them lots of weight, and we want to minimize the little differences. And so, for example, notice in the light treatment, for dish number 12, we have 18 seeds that germinated. And the mean for the entire set of dishes in the light treatment is 18.4. So that's an absolute difference of 0.4. When we square that 0.4 difference, we get a value of 0.16. We've actually minimized that difference a little bit because 18 might just simply be sampling error compared to the mean. However, if we look at Petri dish number 16, there are 12 seeds that germinated. That's a difference of 6.4 from the mean, and that's quite a large difference. And we want to give that extra weight because that's where a lot of the uncertainty is coming from in this mean. And so 12 minus 18.4 is 6.4. We square that, we get 40.96. So we're maximizing the big differences and minimizing the little differences when we do this step called the square difference. All right. The next step is to add them all up to find the sum of the square differences. You'll see this also just called sum of squares. And so here we have 158.4 and 98.4. So right away, students and of course us here in this presentation can start seeing that there's quite a lot more uncertainty in the dark treatment than in the light treatment. 158 is quite a bit larger than 98.4. So this gives us a sense of the quote distance the measurements are from the sample mean when we take this step. What we really want to know, though, is the average square difference, and that's where variance comes in. And so, so the variance gives us this average square difference, but notice that in order to calculate variance, we divide by the degrees of freedom, n-1. And remember, we lost a degree of freedom when we calculated the mean in the first place. So what n-1 also does, though, is it artificially inflates the sample variance a little bit to be a better estimate of the population variance. And we'll see in a few slides how the sample variance and thus the standard deviation, which comes from variance, constantly underestimates the actual population variance. So we want to inflate that just a little bit to get closer to what the population variance and uncertainty actually is. All right, so we have a problem, though. Once we've calculated variance, there's a problem with this statistic. Not that it's a problematic statistic, because it's a very important statistic, and many different statistics launch from the variance. But the problem is it's squared. And so now all the measurements have been squared. So for example, we have number of seeds squared, plants squared, centimeters squared. If we're not measuring area, that wouldn't make any sense, or grams squared. So we must unsquare the units so we can show the true average difference between each measurement and the sample mean. And then that can allow us to calculate standard error of the mean and 95% confidence intervals, etc. When we unsquare that, we actually then arrive at the sample standard deviation, which is an estimate of the population standard deviation. And so we know that the standard deviation must be in the same units as the original measurements. So we unsquare the variance. So the relationship between the variance and the standard deviation is simply a square. Now, there's a lot more in probability theory about standard deviation that we absolutely don't have time to talk about it. So we're going to move right on to the next descriptive statistic, which is standard error of the mean. If you're familiar with confidence intervals, standard error of the mean is a 68% confidence interval, but it's a very popular uncertainty measurement that you'll see on graphs. And so, whoops, I went a little bit too fast there. So standard error of the mean, it's the result of the relationship between the dispersion of individual observations around the population mean, which we call the standard deviation, and the dispersion of sample means around the population mean, which we call the standard error. And so you'll see in this next slide how that works. So here's a figure that comes from a series of papers published in Nature Methods several years ago called Points of Significance. And I found these to be really helpful. They're open access, and so you can get to these very easily. And so this figure shows the relationship between sampling and sample means in the top part of the figure and the population mean, which is theoretical. That's the symbol mu there. In the middle of the graph, we see the relationship between sample standard deviation and the actual theoretical population standard deviation, which is sigma. And then at the bottom, we see the relationship between standard error of the mean and the standard deviation of the sample means of the population. And so we can see that the standard error of the mean converges on that relationship of the standard deviation of the population divided by the square root of the sample size there. So that's where that final calculation actually comes from. Also notice that in this figure on the x-axis, the sample size is increasing from 2 all the way up to 100. And as the sample size increases, then all of these statistics start to converge on what is actually going on in the population, the mean, the standard deviation, and the standard error. And I jumped the gun and already talked about this one at the bottom there. Okay, so moving on. So I mentioned before this idea of dividing, or dividing by n-1 the degrees of freedom, because if the variance underestimates what's actually going on in the population. And so you can see here that even when we do divide by n-1, we still get an underestimate of the actual that actual parameter, in this case standard deviation, in the population. So that's why that's an important step. If you're interested in playing around more with standard error of the mean, Biointeractive from HHMI has a great interactive that I use with my students. They can go to this interactive and see how this works, and they can play around with different numbers. So I encourage you to do that if you're interested. So we're now at the final descriptive statistic that I use with my students, and that is 95% confidence intervals. These are very popular that you'll see in published papers. And so so this is essentially two standard errors. That's what the 95% confidence interval is, and you can see it in the calculation. So so you see in the red box there, 95% confidence interval equals 2S. So S is the sample standard deviation divided by the square root of the sample size. So it's essentially two standard errors. But it only works for large sample sizes. It only works using that multiplier of 2. If you have a small sample, say the 10 sample size that we have with these imaginary data with these Crofton seeds, then we actually have to use a different multiplier. And so you need to be careful with your students. If they're using these shortcuts, they may be underestimating the actual uncertainty that's going on in their samples. And so for samples smaller than 20, you actually have to go to a t-critical table. And I have an abbreviated one here in the lower right in purple. So we have a sample size of 10 in these imaginary data we've been looking at. And so that's 9 degrees of freedom. And the critical t-value for 9 degrees of freedom is 2.26. So notice that is larger than 2. And that results in a larger 95% confidence interval than we would have had we used the shortcut. And so using the shortcut with small sample sizes actually gives us a false sense of certainty in our means that we're using to say something about the population. All right, here's another figure from these points of significance papers that I really like. So this figure on the left in A shows how we can interpret 95% confidence intervals. So notice that we have a theoretical population mean, mu, right down the middle, and we have all of these different simulations that we've run with a sample size of 10, and all of the 95% confidence intervals that have been calculated. And so notice that almost all of them capture the true population mean, except for 2. And so that's what's really important to remember about 95% confidence intervals, is that they tend to capture the true population mean about 95% of the time. And then on the right is the relationship between standard error of the mean and 95% confidence intervals. And so notice that as you decrease in sample size, the 95% confidence intervals really start to inflate. And that's important for students to remember. So when we write about the results of our uncertainty using these confidence intervals, what I often see is students doing it incorrectly. And so because they're called confidence intervals, it's really easy for students to say incorrect things like, I am 95% confident that the true mean lies somewhere within the error bars, or for standard error of the mean, I'm 68% confident the true mean lies somewhere within the error bars. They might even say if the standard error of the mean or 95% confidence interval error bars do not overlap, the means are statistically different or significantly different. And so it's incorrect to actually say that. You would want to say this instead. The error bars have a 95% likelihood of including the parameter, in this case, population mean, that is being estimated. Or if it's standard error of the mean, the error bars have a 68% likelihood of including the parameter. in this case, population mean, that is being estimated. You might also say my error bars either captured the true population mean or they didn't. I can't be sure. And you could say non-overlapping 95% error bars are a good indication that the means are significantly different, but it doesn't guarantee that they are in fact different. Here's a third figure from these points of significance on the left, and both of these figures are generated with simulations using sample sizes of 10. On the left is the standard error of the mean bars and how they relate to each other at different probability levels. And so notice that they don't overlap even with a p-value of 0.1, but at a p-value of 0.05, the second bars down, you can notice that there's about a standard error of the mean between the two error bars when you're at the 0.05 level. On the right, notice that the 95% confidence intervals can have quite an overlap, and you still have statistical significance between them. But again, I caution you not to let your students claim that they have a significant difference between two means by just looking at these error bars. They would need to do some kind of an inferential statistical test like a t-test, which we won't be talking about in this very short talk. Okay, so that was a quick romp through calculating descriptive statistics. I remind you again that we're trying to make estimates about these populations of possible measurements, and the population parameters are unknown to us. So we take samples and we use those samples to make inferences and predictions, but our samples are full of sampling error, and we need to quantify that error, and that's how we do that. And so with this knowledge, our students can move forward and become themselves policymakers and understand figures like these that are published in guidelines for them. And if they read the small print, they would realize that these are 90% confidence intervals that are actually being used in the IPCC 2014 report, but you'd have to look deep into the footnotes and the figure captions to really understand how to interpret error bars like these. And so the last thing I want to talk about in the last couple of minutes is data visualization techniques. So Jason has used a very traditional method for visualizing his data. These are column bars with error bars, and I said at the beginning, these error bars, he's using our standard error of the mean, and these are very traditional, but I think we can help our students do even better and really show what's going on with our samples. And so that's what Kimberly is doing. So she has, as I said at the beginning, on the left, she has a box of whisker plots for each of her three treatments. In the middle, she has means as big pink dots, and her error bars are 95% confidence intervals. And then she has what are called stacked dot plots. So she's showing all of her measurements with a little bit of jitter so that she can see how spread out her measurements actually are. And this is really helpful. It's far more data transparency with figures like this. And I encourage you to encourage your students to create figures like these, because we can start seeing things that we might not see if we were just using simple means with error bars. So for example, in this set of data, here even though we have a significant difference if we run a t-test between the control and the patient group, this group of points, these 9 points out of 22, are actually below the mean of the patient group. And so if we hadn't visualized the data this way with these dot plots, we wouldn't see that that we've got some strange things going on with our sampling. We might want to resample or increase our sample size, or try and figure out what are those 9 measurements and why did they end up so low if the entire group is significantly different than the patient group. These kinds of data visualizations come from Data Classroom, which I started using this year. And in this period of online learning and quarantine, this has really saved me because an app like Data Classroom actually teaches statistics to the students. And so so if you're interested, you might want to check out Data Classroom. So wrapping it up, what is the role of uncertainty in science? Well, science is the pursuit of accuracy in our understanding of what's actually going on in the natural world, but there will always be some level of uncertainty. And so one of the most important things scientists do is quantify and report the uncertainty of their claims and predictions so that we're doing good science, not bad science. And that is my story. Thank you very much.
All right, thank you so much. That was a lot packed into a half hour. So we appreciate what a great job you did in summarizing all of that for us. So we have a few questions from the audience that we'd love for you to address. The first question we have is, what software do you recommend students use? This person says, I've used TUVA, Tuva Labs, and my students appreciate how easy it is to use. What do you recommend?
Well, I've actually never heard of Tuva Labs. I started out using Excel when I came out of grad school, and then moved into Google Sheets when we became a Google school district. But I've been really thrilled with Data Classroom. It's super easy, and it teaches students how to make tidy data tables that are really easy for computer analysis. It teaches them statistics. And full disclosure, though, it's not free, but it's really been a lifesaver for me, especially in these last few months. And of course, they're graphing calculators. Some of the kids, they already know how to work with data tables and their graphic calculators, and all their graphic calculators can do statistics. They just don't know how to interpret the statistics that are returned in their calculators.
Okay, great. Thanks, Paul. What is another question from the audience? What is the difference between descriptive and inferential statistics?
Very good question. So descriptive statistics are simply describing the sample in various ways. And so the sample mean, the uncertainty in the sample, so the confidence intervals, etc. Inferential statistics allow you to infer something more about the population, and so when we sample, we're sampling from these populations that statistically we are assuming to be the same, and then we want to know with inferential statistics is how different might our populations actually be, and so the inferential statistics are things like t-tests, which can tell us whether or not there's a significant difference between two means, or analysis of variance, where we have more than two treatment levels, maybe 3 or 4 or 5 different treatment levels. Chi-square is an inferential statistical test. Regression analysis, those are all inferential statistics.
Okay, thank you for the explanation. Okay, next question from the audience. Where can you find statistics resources online if you're not currently taking a course in school? So it sounds like this might be from a student, but all parents and also teachers would love that advice to guide their own kids and students.
Yeah, well, actually, honestly, I do a lot of Googling when I have my own questions. And I go on, believe it or not, Facebook to my professional Facebook groups, like the National Association of Biology Teachers, and I just ask questions. And there are so many people out there, hundreds of people out there that have answers to a lot of my questions. And I also just encourage you to contact me if you want. I'm pretty easy to find, and I'm happy to help.
Thanks so much, Paul. We appreciate that offer. The other place that folks might consider is walking down the hall to the math department at your high school. I think that math teachers, if a kid walked in and said, I'd like to learn some statistics, boy, would they be excited. So that's another resource everyone has.
I have walked down to the math department myself and asked for help.
That's great. Okay, great. Okay, next question. How important do you think it is for students who want to do research to take an AP statistics course?
Very good. So I have students that are in my science research class and in my biology 2 class that are also in AP statistics, and AP stats I think does a lot with probability theory, which I actually stay away from in my science research class. So my goal is just to show the students the tools and help them understand how the tools work and how to interpret the results of the tools, so that they can make sense of their data. What a class like AP Statistics does is it digs really deep into even more what's going on behind the curtain of statistics. And as I mentioned, AP Stats digs deep into probability theory. So it's more than I want to. I don't teach a stats course. I teach a, a science research course, and statistics are the most important tool we have.
Okay, thank you. And I saw another question on here. What you obviously teach at the high school level. What would you expect in terms of statistics for 6th, 7th, or 8th graders? Do you have any experience, or what would be expected of them?
Yes. So I have a pretty good relationship with our feeder middle school, and all I ask of our science teachers there, our math teachers, is that the students know how to square and multiply and take square roots and add and subtract, because that's really all statistics are. When our students get into the 8th grade level, into their earth science class, I've worked with our earth science teacher, and she does have them do some descriptive statistics, some error bars and things, and they may or may not remember it by the time they get to their to high school. But we have a pretty good vertical team, and that's so important, is that you're talking with your feeder schools about what students need when they get to you. So if they've just had just a little bit of a taste of these kinds of calculations, I think that that can go a long way.
Okay, thank you. All right, we have another question. What do you do if you suspect an outlier in the data set that is due to measurement error? It sure affects the standard deviation and the confidence interval.
Well, what I tell my students is that's often where the most interesting stories are, is those outliers. And in fact, you can look at the history of science, and sometimes it's the outlier that has produced the most incredible discovery. It's that funny point that you just can't get rid of, that doesn't make any sense. I think that's where we discovered RNA interference. In fact, is something funny was going on with these samples, and so I tell my students to don't disregard the outliers, don't let them annoy you, chase them, and try and figure out where those outliers came from. Of course, repeat the experiment, and if the outliers disappear, well, then good for you. But if they remain, then there might be something really interesting going on. So that's my advice.
Yeah. I remember when I did research when I was in college, I had an instance like that, and I told my supervisor, "Oh, please disregard that. I messed up on that one." And it turned out that that particular data point was the answer to what I'd been searching for all summer. So you never know when that'll happen. Okay, let's see. We have time for a couple more questions. This question is from someone at the 8th grade level, a teacher. At the 8th grade level, we teach students about sample size, number of trials, and types of error. But stats are pretty limited to means and correlation coefficients. Do you have any recommendations on anything else we should tackle?
Well, let's see, means and correlation coefficient. Correlation coefficient because students are doing lots of scatter plots. I'm guessing, but I think students can handle the idea of error bars if it's scaffolded well, and if it's taught in a very stepwise, methodical way, and students are just doing it over and over and over again. I think they can start to wrap their heads around error bars. So I think that would be one addition at the 8th grade level. That's what we have our 8th grade science teachers doing in our feeder school, and it's really helpful. Even if the kids don't remember what they've done, by the time they get to high school, there are some synapses back there in their brain that they might be able to access with that memory.
Yeah, and I will say that it's also the same for a lot of teachers out there. I mean, you know, you've learned the statistics at some point in your career. Obviously, you've done it before, but your presentation is one of the most popular sessions at our Research Teachers Conference, because over the years, if you don't use it, then you lose some of it. And so it's really important not to be intimidated by it or embarrassed that you've forgotten some of it. If you just sit down and go through it, watch this presentation again, ask for help from the math department, then it'll come back to you eventually.
Mm-hmm.
All right, one last question from the audience. Let's see, what statistics can be done with Western blot analysis results?
You're asking a bird biologist. I don't have an answer to that question. Yeah, I would have to see the data, the actual measurements. I don't teach our biochemistry content, so I'm really sorry, I can't help with that.
That's all right. Well, I will say that we have a lot of teachers that we bring together at the Research Teachers Conference who ask these kinds of questions of each other. It's a great way to get that kind of feedback from each other. What was, as we kind of wrap up here, what was your experience at the Research Teachers Conference presenting this session to those teachers?
Oh, it was really wonderful, because as you said, Caitlin, the teachers, they really want to figure this out. And I had teachers saying, I haven't thought about this since graduate school, and I really want to figure out how to teach this to my students. And yeah, just put your guard down and open yourself up and become a student again. I'm constantly making mistakes and learning from my mistakes and being corrected by my colleagues, and you just have to be humble and be that lifelong learner that I think all good teachers are.
Thank you. All right. We only have about 1 minute left to answer a question. We do have one other question from the audience, and it might be too long for this, but explain your process of looking at a graph's descriptive statistics when you encounter one in a paper. I'm guessing perhaps that might be one for our audience to email to you.
Yeah, sure.
Okay.
Yeah.
Thanks. We appreciate that. Well, thank you so much, Paul. It's really been a joy to see you again, and for you to give us this overview of statistics. We really appreciate it. I do want to say that currently the lottery for our Research Teachers Conference is open. We bring in 200 teachers every year to Washington, D.C. The conference is teacher-led, so teachers just like you in the audience, just like Paul, are leading the sessions, because of the society, we really believe that you are the experts in leading students in STEM research. We do the very best we can to bring you together, especially this week at virtual Regeneron ISEF, and we hope that in doing that, we are able to support you in the good work that you're doing with students. So thank you very much for joining us. Thank you, Paul, and we hope you all enjoy the rest of the week.
Thank you.